Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Lately, I've been having a bit of a busy month. I don't exactly need to excuse myself in front of anyone, but at the same time, I feel like it's nice to let you know when I have moments when I can't create anything new and I can't upload new videos. Fortunately, this period has passed already, so I'm working hard towards recovering time and doing some more work in the realm of electronics and coming with new videos. In today's video, I would like to show you some experiments, some more experiments that I've done with coils, because I've done experiments in the past as well. As I'm continuing to learn about DC-DC converters, about switch mode power supplies in general, I am discovering new things and I am realizing new things that I didn't know before. So I'm making this video to show you what I've realized in the few weeks that has passed. So whenever we deal with DC-DC converters, obviously we need to use coils or inductors, call them however you want. Now, there are three ways of obtaining those coils. Either we can buy them from the market, and we can buy the complete coils. Basically, we go to an electronics component distributor and we browse through their components and we select the kind of coils that have the right inductance for what we need and the right maximum current for what we need. The second option would be to still go to the market, but buy only the core and the copper wires and create the coils ourselves at home. And the third option, which some people, myself including, find very easy, is to simply recover coils, cores and or copper wires from older devices. Now, if we find ourselves in the first category, in the first option, when we just go and buy from the market complete coils, then we will simply search for the desired inductance, desired maximum current or working current, and that's it. We simply buy those components with money. However, if we find ourselves in situation number 2 or 3, we will need to perform some tests to determine not just the inductance of a certain coil, but also the maximum current that that coil can work at. Because it's pretty much useless if we have a coil of the right inductance for a certain project that we're working, but that coil cannot work at the amount of current that we need her to work. Okay, and this is actually a much bigger requirement, a much more important requirement than the inductance. The inductance can potentially be larger, sometimes even smaller, not by a lot, but definitely can be larger than what we have calculated. However, if the maximum current of that particular coil cannot reach the limits that we want, then our DC-DC converter will simply not work. And various things may happen. Typically, if we use a proper control circuit, then the DC-DC converter will simply stop working. So this is what I will show you in today's video. I will show you a series of tests that I have done on coils, both on a few known coils as well as some some recovered coils, and some coils that I created using some cores that I had lying around, and some copper wire. And this is what we will go through so that we can better understand how to do this test, why, and how do our results will look like. Okay. Now, before we dive deeper into today's topic, please allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com. The link is in the description. Thank you, PCBWay, for sponsoring this video. And now let's move on with seeing what kind of circuit we need to have in order to test our coils, and then move through a whole bunch of tests that I've done, quite a few of them with quite a lot of coils. So stick around if you're interested in this topic. So a while ago, about 6 months ago, I made a video called Better Replacement for 555 Timers. I will link this video in the description. In this video, I showed you how we can replace the 555 timer with a very cheap and simple comparator, LM393 or 339, it's electrically the same, in order to create things that even 555 timers can't do, such as a constant frequency, variable duty cycle, a stable circuit. Okay, I'm not going to go into great details about how this works because I've explained in this video at around minute 21 how such a circuit would work and would provide on the output essentially a PWM signal with variable duty cycle that we adjust through a potentiometer, and constant, more or less constant frequency, of course, that we can also adjust if we choose to use some potentiometers instead of fixed resistors. Today's circuit that I will just mention briefly is essentially such a square wave signal generator that has a small circuit in order to drive a P-channel MOSFET, and the rest looks similar to a buck converter essentially. Okay, so we have a signal generator, we have a couple of potentiometers for adjusting the frequency. I've put 2 of them just so that we can have both a coarse and a fine adjustment, and also another potentiometer for adjusting the duty cycle. The output of this circuit, which again is formed with 2 LM393 open collector comparators, the output is sent to a combination of 4 bipolar transistors, okay, that will later offer a relatively high current on the output and a rail-to-rail swing of the output voltage. It's not 100% mandatory, but I like it when, you know, my signal generators can go rail-to-rail. This so essentially there are just to quickly explain what's going on in here, right? We have the output of a comparator, which is essentially the collector of another bipolar transistor. this output is either being pulled down to the ground or left floating, and resistor 5 here will pull this output up to the positive rail. This signal gets fed into two different bases of two different transistors, NPN transistors. Both of them will either turn on or turn off at the same time, and each of them is commanding the base of another bipolar transistor, but this time one that's NPN and one that's PNP. Essentially, when both of these lower transistors turn on, they pull the bases down to the ground, then the NPN transistor on the right side will close and the PNP will open, essentially making the output have a logic high. When these two lower transistors will turn off, then the PNP transistor will turn off as well, and the NPN will, from the right side, will turn on, will pull the output down to the ground, and on the output we will have zero logic, or almost 0 volts. Okay, so this is how we have a simple, rudimentary, but good enough square wave generator with rail-to-rail output and adjustable duty cycle. We will be using this to basically turn on and off a P-channel MOSFET. In my case, I chose AOE 423. Why? Because it's a pretty good P-channel MOSFET. It can resist 30 volts. Honestly, I do not need more for these kinds of experiments, because I chose to power everything from a 12 volt and 20 amp power source. I took a power source from an old PlayStation 3 that was broken, but the power source was still functioning. Those of you who know what I'm talking about know that those PlayStation 3 power supplies, they can offer more than 20 amps on the output, which I find good enough to test a wide array of coils. Okay, and this P-channel MOSFET, since he can resist 30 volts, it's more than double the voltage that we have on the power supply rails. Okay, and what's great about this model of MOSFET is that we can have up to 70 amps of current flowing through him. Of course, he needs to be placed on a form of radiator to dissipate heat. However, the heat is not going to be all that big, because at 10 volts gate to source, or well, minus 10 volt gate to source voltage, the datasheet tells us that drain to source resistance will be 8 milliohms or less. So it's almost never going to get warm. At least if we will be using him in just switching region, either fully on, fully off. So this is a pretty good P-channel MOSFET to have in general, but especially in these kinds of tests that we are trying to perform. Okay, so this signal generator essentially feeds directly the grid of the gate of the MOSFET. Okay, when we have high voltage, the MOSFET is turned off. When we have low voltage on the signal generator's output, the MOSFET is turned on. Okay, and we can also monitor this with the one of the oscilloscope channels, and I will show you in a moment why we want to monitor this thing and how does it help us. This put channel MOSFET needs to turn on and off, basically needs to inject a current into the coil that we are trying to test. Okay, in this case, this device under test inductor. And unlike a proper buck converter, the output of this coil does not need to be a capacitor, but rather a very small resistor. I chose 100 milliohm resistor, 5 watts, because this is a standard value of power and resistance. It's small enough so that the extra resistance is having minimum impact on the coils that we are using, because of course any resistance in series with a coil will affect the performance of the coil. So 100 milliohms is low enough resistance so that we don't really care about that. But at the same time, it makes things easier, because every amp of current that will flow through this resistor will produce 100 millivolts across the resistor. So by measuring, taking a look with the second channel of the oscilloscope at the voltage across this resistor and setting the number of volts per vertical division to 100 millivolts, then we basically have 1 amp per division, and it makes current readings a lot easier to perform. Okay, and just like in normal buck converters, we need the so-called freewheeling diode. We need an ultra-fast diode or a Schottky diode before the coil, before the inductor, so that when the MOSFET gets turned off and the inductor is charged with electromagnetic energy, he will start to generate his own current, and this current needs to be able to flow through the inductor, through this small resistor and back at the inductor. Okay, we want this loop as small as possible, as short as possible, and we don't want anything else. We don't want to store energy anywhere else. We don't want to charge any capacitor. We just want to inject current into the inductor and then allow the inductor to discharge. Okay, so I have chosen 6 diodes placed in parallel. Here I have only drawn 1, but in reality for me there are 6 diodes in parallel, model FMLJ12. No particular reason, these were the diodes that I had at hand. These diodes can resist 200 volts reverse voltage, which is a lot more than we need, but they can resist 5 amps of current each. Of course, if you can just buy one of those diodes that can resist 20 amps or 30 amps. You don't need to put 6 in parallels like I did. I did that just because I didn't have any other diodes that can resist high currents, and even so, because these are only 5 amps and I wanted to go up to 20 but still be safe, I chose to put 6 in parallel. So theoretically they should be able to pass 30 amps of current at best, or at least 20. Okay, this is the logic behind these diodes, and this is the entire circuit. Okay, it's not rocket science, it's not such a big deal. You don't really need this entire signal generator. If you happen to already have a lab signal generator, a proper signal generator, okay, for laboratory usage, you can use such a function generator or a signal generator. I have placed this circuit for those of you who don't have a proper signal generator. It doesn't make sense for you to pay, I don't know, $200 or more on one just to be able to have a square signal with PWM, with a duty cycle adjustment. Okay, you can just create this and you're gonna be a lot cheaper. So that being said, this is the circuit that I have used and that you will also need to use in order to test all sorts of inductors and coils. So now let's get started and let's take a look at waveforms on the oscilloscope. Again, the waveforms that we will be using are these two ones. One is the output of the signal generator himself, which in my case goes from 0 to 12 volts, and the other is the signal across this 100 milliohm resistor, which basically gives us 100 millivolt for every amp of current that flows through the coil. Okay, and let's see. So in order to have a reference point, I decided to test first some coils that I knew, some coils for which I had the characteristics beforehand. So first coil is a 1 millihenry inductor, 400 milliamps of working current, okay, that you can buy from the market. It's about 150, it's about 15 euro cents a piece. And well, since the working current is 400 milliamps, so less than half an amp, obviously we won't be able to inject a lot of current into the coil. So here we have 50 millivolts per division, per vertical division. Essentially this means half an amp, okay, and this is the current that theoretically is maximum for this particular coil. Now what do we see here? We see with blue, but it's mostly covered with yellow, we see the square wave signal on the input, okay. With yellow we see the voltage across this resistor here, this 100 milliohm resistor. And we need to make abstraction of a few things. First of all the noise, okay, that came from all sorts of other things that I had lying around, my PlayStation 3 power supply, maybe other sources as well. So all of these small spikes need to be visually filtered out. I already enabled the bandwidth limitation on this channel, but there were still some spikes left around here, and these bigger spikes that form naturally when we are switching current into the inductor. Okay, so as we can see, these vertical pairs of spikes, these happen when the MOSFET gets turned on and then off, so we will have to ignore them as well. What is left is essentially a triangle wave that is around here. I'm gonna draw with red on top just so you can, have a better view of what I'm talking about. So the waveform that we care about is here in the middle. Basically, you have to visually, make an average of all of these values that you see here. In some later pictures, I actually made an average with the oscilloscope himself. So this is what we see here. Okay, so if we have 50 millivolts per division, therefore we have half an amp per division. So this is what we are supposed to see when everything's fine. We are supposed to see a ramp up and a ramp down of current. The ramp up happens when the MOSFET gets turned on. The MOSFET gets turned on very shortly, very short amount of time in my case. And then the MOSFET gets turned off and the coil discharges herself, and we have the ramping down of the current. Okay, Whenever we start these experiments, we always start with duty cycle 100%. So before you do anything, don't connect any coil, leave here no coil connected, and just take a look at the signal and adjust the duty cycle all the way up to 100%. 100% duty cycle for a P-channel MOSFET means that the MOSFET is turned off completely. Okay, so we start from 100% duty cycle and we move down. The smaller the duty cycle, the more current we will be injecting into the coil, and vice versa. This is basically in reverse to how in most other circuits we would be doing. In most other circuits we would start from 0% duty cycle and move upwards. Anyway, okay, so this is half an amp, okay, through a 400 milliamp working current coil. Then I started to basically I increased the, or I should say I decreased the duty cycle, which made the MOSFET turn on more time and inject current in the inductor for a longer period of time. And what we see is that the current ramps up a bit more and then goes down, but starts to form, it's no longer a straight line down, starts to form sort of like a semi-curve like this, okay? This is a good indication, and we will see more clearly in the next coils. This is a good indication that we have exceeded or we are starting to exceed the maximum current that the coil can support. Again, this is a 400 milliamp coil, working current coil, and right here we have a peak of 1 amp. So more than twice as much as she's able to work with, okay? And if we go even higher than that, we see this even better, okay? We have a sharp increase, and then the decrease is very steep, and then a linear region, and then goes down and stabilizes at around 400, 500 milliamps of current, okay? And this is a good way of telling that yeah, that's the maximum current that the coil can support. Moving on to the next coil, 390 microhenry. This particular model, working current 1.4 amps. Okay, it's a more expensive coil, 51 cents per piece. And well, since working current is 1.4 amps, we should easily be able to go up to 2 amps, maybe more. So this is what we see here, 100 millivolts per division, which means 1 amp per vertical division. Okay, and we are here at about 1.5 amps. Okay, we're ramping from a little over 1 amp all the way to 1.5 amps, and then the ramp down is linear and goes only to 1 amp, and then goes up again, and so on and so forth. So this is a good, healthy graphic that we want to have for such a coil. And of course, if we start to push more current, the graphic will go up, but the more current we want to push, the more we start to experience the same kind of semi-curved discharge of the coil that indicates that we have passed the maximum current that we can work with that particular coil. Again, this is a 1.4 amp coil, and here we have 3.5, so this peak right here is at about 3.5 amps, so more than twice the working current, okay? And if we take a look here, this is almost 2 amps of current. So again, this this proves the specifics, the specifications of this particular coil. Third coil, similar coil, but smaller current and smaller inductance, or only 100 microhenries and almost 1 amp of working current. Okay, and again 1 amp per vertical division. And what we see here is again the normal healthy graphic. Then as we try to push more and more current, we see that the downward graphic gets rounder and rounder. Okay, so from a straight line here we have a very slight curvature, and here when the current on the charging cycle has gone really up, so we have kind of this ramping up graphic that is at 1, 2, 3, 4, 5 amps, 5 times more than what we can work with. Then we see that the discharge graph also has a very steep decline, and then this sort of semi-curve shape, and eventually stabilizes at around 1 amp. Okay. Fourth model, this is a higher current inductor, 150 microhenry, 3 amps working current. And of course the graphic looks nicer. By the way, I forgot to mention, pretty much all of these graphics that I'm showing you here are switched at about 12 kilohertz. I know it's a very low frequency, but I find it easier to see ramping up and down of these coils. In practice, we will never use such a low frequency. We will always use 40, 50, 70, 100 kilohertz, right? And so the ramping up and down will be much smaller. But because I actually wanted to see more pronounced ramping up and down of the current, I chose the smallest frequency that I could set my signal generator, the circuit that I've shown you earlier. Okay, so this 3 amp coil, okay, here is with the maximum current of 3 amps, and then ramping down linearly as she should, and then we push the current further up. We see that well, it's not a problem even 5 amps. Okay, so we start at 3 amps here and ramp up to 5 amps, and then ramp down again at 3 amps. This is still okay. Now I have switched to, so here we had 1 amp per vertical division. Here I have switched to 2 amps per vertical division, and it's the same coil. So we start at 2 amps and we have, we start at 4 amps and we have 6, 8 amps here, okay, and then ramping down, and as we see, we can go up to 8 amps. The ramping down, however, starts to look a little bit curved, okay, but eventually goes down to 4 amps, which is nice. It's more than the 3. Okay, again, this is a 3 amp coil. Right, and this is an even higher point. Okay, so I've shown you this graphic, and now this graphic, this goes even higher. This goes up to 10 amps, or above 10 amps a little bit, 11. But then because it's way more than 3 amps working current, we see that on the discharge phase we have a very fast drop of the current, then slightly more curved ramping down. Okay, and a similar coil but even higher current, 5 amps, 220 microhenries at 5 amps, this particular model. These were more expensive. This is €2.5 a piece. The previous coil was €2 a piece. And let's see how this 5 amps coil does. I kept the oscilloscope at 2 amps per division because of course 1 amp is just too little. And what we see here, we start at 3.5 amps, and we move up to some 5 amps or so, 4 point something. The ramp down is linear as expected. And then I really pushed things really hard. I'm starting at 2, 4, 6, around 6 amps, and I'm going all the way up to some 12, maybe even above 12. And as we can see, the coil is still working pretty well. We have a very fast discharge in this short amount of time, but then the current manages to discharge slowly, linearly, and to reach the same point as when we started. So overall it's still okay, even though this small point is above 6 amps and the working current of this coil is 5 amps. Okay, when the working current is a certain value, that coil definitely can go above than that value. Now, so far we've only been playing with relatively high values of inductances in the order of hundreds of microhenries or more. This particular circuit and this particular method is gonna prove to be more difficult with very small inductances, like in the order of microhenries. It's not completely impossible, but we will need to increase the frequency, the switching frequency, just so we can see the ramping up. And overall it's going to be more tricky because, you know, the entire switching thing, the entire switching process needs to be quite good so that we don't put the MOSFET into linear region, because then he will dissipate a lot of heat. The MOSFET needs to be placed on a cooling radiator, as well as the diodes at the output. So just to show you how 3.3 microhenry looks like, I have gotten this model that says it's capable of 15 amps of working current. 2.5 euros a piece, so again not very cheap, but because of the very small inductance and because I didn't want it to go up to a higher frequency, yeah, I kind of had problems actually you know, performing tests on such a coil. As we can see, the ramp for the charging of the coil is very steep. It takes a very short amount of time because, of course, we have small inductance, and yeah, and overall I couldn't really measure the maximum current, and I couldn't really see the ramping down, just like in the previous coils. Okay, and this was the final coil that I knew, a coil that I bought from the market and I could use as reference. From now on, all that I'm showing you are all sorts of other coils that I've recovered and or created myself. So next coil is a 10 millihenry inductor that I've created using one of those ferrite toroids that are typically placed on a cable to suppress electromagnetic interference. Those are not made for you know, power inductors, but they can still work at smaller currents. So I have set here the vertical oscilloscope on 10 millivolts per vertical division, which means 100 milliamps per division. Okay, and we see that the 10 millihenry inductor created with such a ferrite core can only work with a few hundred milliamps at best. So what we have here is kind of like this, basically. Okay, we have 100, 200, about 250 milliamps peak current. And here we have about 400 milliamps peak current, but this descending curve tends to be a bit too curvy. And if we insist on you know, pushing higher currents, then we clearly see this downward curve and this really fast, even though we have 10 millihenries, which is a relatively high inductance, the current is dropping pretty fast, and it's eventually stabilizing somewhere at below 100 milliamps. That's because this particular kind of ferrite core is not made for power inductors. Next coil, some coil that I've recovered from a device, from a semi-broken device. I know absolutely nothing about her. I didn't even measure her inductance, but doesn't matter because, like I said, we want to know the maximum current that can pass through such a coil. So first test with 1 amp per vertical division shows me that you know, we have a bottom of 2 amps and the ramping up goes 3, 4, 5, 6 amps. The ramping down is pretty linear, so this is a pretty good coil for a pretty high current coil. Okay. Another coil that I know nothing about, but this is one that is a bit bigger in size. The diameters are a bit bigger. Okay. And also it's an even bigger current coil. I have 2 amps per vertical division, and we see here 4, 6, 8, 10, and we have a little bit of a faster dip, but then more or less linear ramp down all the way to 4 amps. So this is clearly, okay, this is higher current, this is lower current, going from 2 all the way to 6 amps and then back to 2, and we see a much more linear descent, okay, than in the previous one. But nevertheless, this is a pretty high current coil. Okay, we see here 5 amps per vertical division, and we see we have started from about 8 amps and we have gone all the way here. Let me see, here is 5, 10, 15, 20, more than 20 amps of peak current, and then linearly, well, it's all the downward curve is already a bit too curved, so Obviously, we wouldn't use such a coil quite at 20 amps, but the coil herself has some nice potential. Okay, so can easily be used at, I don't know, 10 amps or so. We see that the current goes back to about 8 amps where we started, which is nice. Then I moved on to create my own coil with an unknown ferrite core. I just took a toroidal ferrite core. I wound 17 turns of wire created with 4 different wires placed in parallel to minimize the skin effect. And in the end, I chose to measure the inductance just so that I see, you know, what kind of coil I've created. Around 80 microhenry, give or take. However, due to this ferrite material, this ferrite material doesn't seem to be, at least at these lower frequencies, doesn't seem to be capable of working with high currents. I have 1 ampere vertical division, and we see here that ramping down is pretty fast, and then goes down to 0. Ramping up to 2, maybe even more than 2 amps, maybe even 3 amps, but then ramping down is really fast and goes down to 0. This also is a good indicator of the fact that these ferrites are made for higher frequencies. Okay, even higher current, so ramping up is this all the way this up, so 1 2 3 4 5 6 amps going upwards, and then ramping down is really fast, going down to 0. So yeah, so such a ferrite is not good, not really all this good with either low frequencies or high currents. Then I took another core, but this time a core that I bought from the market, and I'm gonna show you the model in a moment. I have wound 20 turns, okay, and I discovered that in the end I managed to get an almost 2 millihenry inductance, which is quite big. The core is this particular model. I'm not gonna pronounce every letter and number, doesn't make sense. It says permeability 4300. The amplification, inductance amplification factor is 4.6 microhenries, which is quite a lot. And external diameter 25 millimeters. Made by TDK, more than €1 a piece. Now, in case you're wondering what's with this amplification factor, let me quickly explain. So the inductance of an inductor is, well, this is just one formula. Of course, there are others as well, but in order to simplify things, the inductance depends on the number of turns, which is N, and a certain amplification factor, which here is A indice L, which depends solely on the material of the core that we have used. So basically, if we take 2 or more cores that have the same inductance amplification factor and we wind the same number of turns on them, we will get inductors with exactly the same inductance value in the end. Okay, so this is nice because, you know, if we know, or if we measure the inductance amplification factor of a certain material, then we will very easily know what inductance we can create, how many turns do we need, and so on and so forth. Okay, And from this formula, of course, we can derive the other formulas, because we can just rotate these variables around. We can calculate the amplification factor of an inductor by simply winding a certain number of turns on that particular material, measuring with an LCR method the inductance, and then calculating this division. Or if we know the inductance that we want to obtain in the end, and we also know the inductance amplification factor that's particular to our material, to our core, then we can calculate the number of turns that we need in order to obtain that inductance. Okay, so this is why sometimes you see this value written in henries, well, submultiples, nanohenries, microhenries, for cores that don't really have a coil wound around them, but they still have this. This is because you can use this kind of formula to determine in the end what kind of inductor you will have. Okay, so like I said, I want 20 turns on this particular model of core, 2 millihenries of inductance in total, and apparently this kind of core is not made for high current. Okay, the ramping up is pretty fast. Sorry. It's pretty fast, but the ramping down is also fast and gets down to almost zero really fast. So I couldn't make a high current core coil with this core. Okay, and I also zoomed in quite a lot here to see the ramping up, which is very difficult to see. Okay, it's here. And the ramping down, it's like this. So yeah, so my best guess is these kinds of cores are made for something else, are designed for creating inductors for something else, not for DC-DC converters or switch mode power supplies in general. Yet another of those blue cores, but this time one that is smaller. I turned only 10 turns of wire around this core, because this core had a small inner diameter, small outer diameter. So yeah, I only got 500 microhenries, which is still a pretty good inductance to have, but smaller than the previous one. This is the core. Okay. We don't have here, but of course, if we would look in the documentation, we would definitely get to see that amplification factor written somewhere. Here they only says that it's core model T38. Every ferrite or iron powder core has a certain numbering system, and if we search for that numbering system, we will find what that is good for. Okay, and once again, the coil that I've managed to obtain with this core was not particularly a high current capable core. I believe this coil could be high current if we would increase the frequency a lot. So we have 20 microseconds per division. I believe if we use above 100 kilohertz, so less than 10 microseconds, we would be able to, you know, work with maybe 2 amps here, because we see the the ramping down goes and hits 2 amps after about 10 microseconds. from when the MOSFET gets turned off. Okay. Also the turn on is kind of not linear, so yeah, these cores are not made for switch mode power supplies. And last but not least, I have a core that I bought from someone who recovered some coils from a device. Apparently it's a Siemens N28 model core. This is actually made from two different pieces that are put together, and they they form a sort of a clamshell. This model of ferrite core has 400 nanohenry amplification factor, which is quite a lot, which allows us to, you know, have pretty high inductance values. I wound 16 turns of wire around this core, and in the end I measured this to have about 90 microhenries of inductance, which makes sense, which is normal and makes sense. Okay. And yeah, apparently I can have up to 1 amp with such a core. So apparently this core can be used for DC-DC converters, switch mode power supplies. If we go way above 1 amp, then the core is no longer able to function properly. Okay, we see the ramping up around here, and then a very quick ramp down, and a more linear ramping down, going all the way down to some half an amp or so. Anyway, I believe it's safe to say that this coil can work at 1 amp of current continuously. And in order to actually test if this is true, I decided to put this coil into a DC-DC converter made with an LM simple switcher. I don't know exactly, I don't remember the model, 2950 something or 2590 something. Anyhow, these kinds of DC-DC converter chips, if they detect that there's a problem with the coil or with anything else, they will simply shut down. So that's a good indication of, you know, when your coil, if everything else is good and works, that's a good indication of your coil not being good enough for that particular current. So I am feeding this DC-DC converter from some 11 or 12 volts input. I have set this DC-DC converter to give 5 volts on the output, and this is what we see here with the right hand multimeter, and the yellow multimeter will show us the current that we will draw with an artificial load. Also on the oscilloscope I have the output of the DC-DC converter coupled AC in order to see only the ripple, because that's only that what we need, what we want to see. And now I'm starting to pull some current. The output voltage remains pretty good, around 5 volts at half an amp. Remember, we have determined previously that this coil can go up to 1 amp only, and that's in theory, and now we are actually putting this theory to the practice. And I'm increasing the current all the way up to almost 1 amp. The voltage is still pretty nice, but the ripple is decent, but from now on the ripple is going to become worse and worse as I increase the current. Okay, and that's a sign that you know, the coil that we created with that magnetic core is struggling to work at currents higher than 1 amp. Now I could go up to about 1.4 amps, however the ripple becomes unacceptably high, more than 300 millivolts. Before we had around 50-70 millivolts, and the waveform of the ripple is also not very linear anymore. Before we had a nice triangle, now we have sort of an U-shaped ripple, which clearly indicates that the coil goes into saturation, and of course that's a bad thing. That's not something that we want to happen. But nevertheless, this proves that these experiments that I've shown you earlier are good and are able to give us an indication of the maximum current that a coil is able to work. And this is going to be very, very important when we will recover coils and want to use them in power supplies, or when we want to create our own coils one way or another. So this is pretty much it. I have talked a lot. I have shown you a lot of experiments. I hope that now you understand these problems better. Thank you very much for watching. Thank you to those who are supporting my work on Patreon. I will come as soon as possible with even more interesting and useful videos on our quest to create switch mode power supplies and to power our house from power supplies that we have created from scratch. So thanks a lot for watching. Don't forget to like and subscribe to this channel if you want to see more of me. And I will see you soon. Bye bye.